Okay, question 10 is a common question about tracers, which we've looked at. So a radioactive isotope is injected into a person's blood stream. It's going to emit some radiation. As the blood flows through the kidneys, the radiation is detected, and they've given you a clue outside the body. So I need something that, there's my body, it can penetrate out of it. So what type of radiation? Well, alpha and beta wouldn't be able to pass through the body, so I need gamma. It would be able to penetrate through. During the scan, the technician needs to take readings for about 30 minutes. The half-life of the isotope is about 6 hours. State why an isotope with a half-life of 6 minutes is not suitable. And the idea is it'll decay by half, so there'll just be no activity left to measure. By the time it's got to the kidneys and doing its stuff, there's too little to measure to give us a good image. So decay too quickly to give a measurable activity. State with an isotope with a half-life of 6 days is not suitable. So now we've got the alternative. It's going to be in the body too long. This will increase the dose and the risk to the patient. So stay in the body too long, this will increase exposure or dose, and that would increase the risk of disease. State 2 ways of reducing risks. So you see this has come up so many times on past papers. So we've got the usual list. So lead shielding for the technician. We can lead shield the walls. We can limit the exposure time. They can move a safe distance away or leave the room or go into an alternative room, go into a lead-lined room, or they can wear protective equipment such as gloves and masks, or another one that I could have put into there, they could wear a radiation badge that tells them their dose. Any of those. Next part, we've got nuclear fission. So we've got our control rods here, and we know they're made of boron, and they'll move down to slow the reaction or the fission rate, and they'll move up to increase the fission rate. We've got a moderator here, and that controls the velocity of the neutrons. So ultimately it slows them down so that we can increase the rate, and then we use the control rods to really sort that part out. So explain how pushing the control rods further into the reactor slows them down. So the control rods absorb neutrons if I push them in further. So there are less neutrons available for the chain reaction, and this reduces the fission rate. The crucial words there are absorb and chain reaction. Next one, the moderator slows down the neutrons, and then it tells us the speed of the neutrons. So the fast ones are at this, the slow ones are at that, and it says calculate the average speed of the slow as a percentage of the fast. So that's just saying work out your ratio of slow to fast, and as we know, any ratio can be turned into a percentage by then timesing it by 100. So it's just taking the right numbers, put them into your calculator. Remember, use that function on your calculator. It'll stop you making daft mistakes. So there we go, 0.013. We've done the slow of the fast and timed it by 100. The nuclear reaction is the first stage in the process of getting electricity. Describe how energy is transferred from the reaction to the next stage. So we've got this part here, we've got our nuclear reactor. Then we know it's going to go into a heat exchanger. Then we know that's going to be transferred to pipes with water that will be converted to steam. Terrible writing, but you get the idea. So that'll be turned to steam, which will turn a turbine, which will then turn a generator. So I'll have magnets spinning around cores of wire. So really, it's just going through how do we get the heat energy here? Is this question? How do we get this heat energy? So our crucial part is, well, the daughter nuclei and the neutrons will transfer kinetic energy to the heat exchanger, to the water. And then the next part is RE equals mc squared. So a small amount of mass is lost and converted to thermal energy according to equals mc squared, and that'll be transferred to the coolant or the heat exchanger or to the water. And there we go, that's everything done.